Welcome to the deep dive. Today we are diving deep into, well, the literal language that powers pretty much all modern artificial intelligence. We're talking about that core challenge, to taking this messy, nuanced, beautifully ambiguous communication we use every day and turning it into something machines can actually calculate with.
Yeah, something they can process.
The technical term for this is word embeddings. And if you've ever had, an AI autocomplete your sentence, or maybe detect spam really accurately, or even translate a foreign language almost instantly, you are using the incredible power of these word embeddings. It's like the alphabet of AI.
That's a great way to put it.
Okay, so let's unpack this. Our mission today is to strip away some of the jargon, really understand how words become these numeric vectors, why this conversion is absolutely essential for machine learning algorithms, fundamentally essential, and also how this whole technique has gone through this really radical evolution, leading to the powerful AI we see everywhere now.
Right. And if we start with the simplest definition, a word embedding is essentially a kind of coordinates system for language. It represents every single word as a numeric vector, so just a long sequence of numbers in a very high-dimensional space.
High-dimensional space, okay.
And the genius here isn't just that it's a mapping. It's that this mapping is really highly structured. It captures semantic meaning, contextual relationships between words, and the immediate payoff, this is crucial for you, the listener, is that words meaning similar things are positioned incredibly close to each other in this vector space.
Okay, that makes immediate sense. Like if I plot car and automobile, they should be like neighbors in this space.
Exactly.
But that raises the really fundamental question. Why convert car into, say, a series of 300 numbers instead of just processing the text car? Why can't the machine just read?
Yeah, that's the key question, because fundamentally, most machine learning algorithms, they're mathematical engines, right? They're built on linear algebra, matrices, calculations. They can't natively understand or process raw text like the letters C-A-R. So if you want a machine to predict something or categorize or translate, you absolutely must feed it numbers. Word embeddings are basically the universal language interpreter that solves that foundational problem.
And here's where it gets really interesting for me, because the numbers don't just exist in isolation. They encode relationships. You mentioned distance indicates similarity. Does the direction of the vector also matter? Is that significant?
Oh, absolutely. Hugely significant. The vectors aren't just points scattered randomly. They are mathematical entities. They have magnitude and direction. And that means the relationship between two concepts, it can be preserved through vector arithmetic. So the movement from one vector to another, that direction, can actually encode abstract concepts like, say, tense or gender or even opposition.
Wait. So you're saying if happy is plotted in one area and sad is maybe in the exact opposite direction across the origin point, that opposition is mathematically encoded?
Precisely, yes. And these numeric relationships, they aren't just designed, they are learned. They're learned by training these models on truly vast corpora of text. Think trillions of words scraped from the internet, books, articles, everything.
Okay, so can you walk us through that learning process? Let's say I feed it all of Wikipedia. What happens first? Does it just start reading?
Well, not quite reading. First, that raw text needs some pretty heavy pre-processing. We break it down into tokens.
Tokens, like words or parts of words?
Usually words or sometimes meaningful subwords, yeah. And then we typically remove common noise words like the A is what we call stop words, and also punctuation. Then the model starts to learn, usually using something called a sliding context window.
A window?
Yeah, it looks at a target word, and then it looks at its immediate neighbors, the context words around it. And it iteratively learns to predict one based on the presence of the other. It's basically a vast, continuous game of fill in the blank across the entire text corpus.
Right. We often try to visualize this in, like, 3 dimensions, X, Y, and Z axes, where maybe apple and banana are close together.
Yeah.
But you mentioned earlier, and this is key, that in practice, these vectors often have hundreds of dimensions. If 3 dimensions give us fruits and maybe opposites, what on earth does the 300th dimension actually capture? Can we even conceptualize that?
That's a brilliant question, and honestly, it speaks to the real power of this representation. While we can't really visualize 200 dimensions mathematically, those hundreds of dimensions capture extremely intricate relationships and nuances. So dimension 1 might capture something relatively simple, like animate versus inanimate. Maybe dimension 50 captures something like formality of usage, and dimension 300, it might capture some incredibly subtle semantic relationship, like, often used with verb X or related to historical events. Think about a word like justice. It doesn't just relate to law, right? It also relates to fairness, equality, maybe even vengeance, depending on the context. Capturing those subtle linkages, those different facets of meaning, requires many, many axes to fully define where justice sits in this universe of concepts.
That really helps explain why these vectors are so foundational.
Okay, so moving to how are these numeric representations actually used? They're the core engine of natural language processing, or NLP. What are the key jobs they perform out there in the real world?
Oh, they're absolutely central to tons of applications. Text classification is a big one.
Like spam filtering.
Exactly. If you're filtering emails, the machine isn't reading the text in the human sense. It looks at the vectors of words like free, win, prize, click here, and it compares the overall vector representation of that email to vectors from known spam emails. Their proximity in this vector space determines the categorization, spam or not spam. Okay, makes sense. And what about something like named entity recognition, NER? How does a vector help identify a specific person or a place or like a company name?
The NER benefits hugely because the embedding, it naturally places related concepts together. So Elon Musk might end up close to CEO and Tesla and SpaceX in the vector space. The model uses the context of the vectors of the surrounding words to infer that a particular sequence of tokens is likely a named entity, even if it's never encountered that specific name before. The neighborhood gives it away.
The application that always just blows people's minds, though, is the word analogy thing. The idea that we can perform arithmetic on concepts, it sounds like science fiction.
It really does, but it's the ultimate proof point, isn't it? It shows this numerical conversion isn't just arbitrary mapping, it's capturing real linguistic logic, real structure. The classic formula, the one everyone quotes, is this. Take the vector for king, subtract the vector for man, and then add the vector for woman.
And the result?
Well, the resulting vector points pretty much directly to queen.
That's just stunning. It proves the numerical arrangement is genuinely capturing conceptual structures, like gender roles or maybe hierarchical relationships.
Exactly. And that same principle of semantic similarity is what drives more complex systems, like question and answering systems. When you ask a search engine or a chatbot a question, the system converts your question into a vector. Then it scours its database, comparing your question's vector to the vectors of maybe thousands or millions of articles or documents. It uses the closest semantic match, the nearest vectors, to pull what it thinks is the best answer.
The success of all these applications, though, it really depended on researchers figuring out the best way to generate these numeric representations in the first place. So let's shift gears a bit and look at the two main philosophies or categories for generating embeddings. The frequency-based methods versus the prediction-based ones.
Right. The frequency-based methods are sort of the historical foundation. They derive a word's representation pretty much strictly from how often words occur together or within documents. The logic is quite simple, really. If a word appears frequently in a certain context, it must be significant in some way. Importance is inferred from frequency.
And the classic model here, the one people might have heard of, is TF-IDF. That stands for Term Frequency Inverse Document Frequency. Can you break down how that calculation actually works to differentiate words?
Sure. TF-IDF is clever because it doesn't just count raw frequency. It assigns a high score to words that are frequent within one specific document you're looking at. That's the term frequency part. But are simultaneously rare across the entire collection of documents, the whole corpus. That's the inverse document frequency part.
Ah, so it balances local importance with global rarity.
Precisely. So, in a document about, say, coffee, words like espresso or cappuccino might get a high TF-IDF score because they appear often in that document but aren't common across all documents on the internet. Meanwhile, super common words like the or and or is will get very low scores because while they're frequent locally, they're frequent everywhere. TF-IDF is really good at telling you what a specific document is about.
But the big challenge with these purely frequency-based models, as I understand it, is they don't capture the subtle relational meaning very well, right? They just count co-occurrence or association.
Exactly. They know espresso is important to the coffee document, but they don't really capture the relationship between espresso and bean or milk or machine in a deep semantic way. And that's precisely why the shift to prediction-based embeddings was so revolutionary. These models move beyond just raw counts. They actively try to capture those semantic relationships and that deep contextual information by performing predictive tasks during training.
Predictive tasks, like the fill-in-the-blank game you mentioned.
Sort of, yes. Instead of just counting, these prediction models learn context. If a model sees the sentence, "the lion hunted the zebra," and then later sees "the lion slept in the tall grass," it learns to associate lion not just with hunted and zebra, but also with slept and grass. It gradually builds a single fixed representation, a single vector for lion that somehow manages to encompass all those different related concepts it sees in the training data.
Okay, so which models really drove this massive prediction-based shift? This was around the early 2010s, right?
Yeah, that credit largely goes to Word2vec, which was developed by researchers at Google back in 2013. Its real strength was its efficiency and the quality of the embeddings it produced. It focused very tightly on learning from the immediate context around each word, just that small window of neighboring words, to build its vectors.
And Word2vec famously had two main architectures, right? CBOW and skip-gram. What's the conceptual difference between those two?
Right. CBOW stands for Continuous Bag of Words. It's trained to look at the context words, the words surrounding a blanked out target word, and predict what that target word is. Skipgram is essentially the inverse task. It looks at a target word and tries to predict the surrounding context words.
Which one worked better?
Generally, skipgram tended to perform a bit better, especially with smaller data sets or for capturing rarer words. The thinking is that predicting the context from a single word is a slightly harder task, which forces the model to learn more nuanced, higher quality embeddings.
Okay, so Word2vec arrives, focuses locally, but then not long after, in 2014, Stanford researchers released GloVe, that's GLOVE, Global Vectors for Word Representation. How did GloVe contrast with Word2vec's approach? Was it doing something fundamentally different?
It was, yes. While Word2vec really only looks locally, at that immediate context, WindowGlove takes a step back and tries to incorporate global information. It specifically analyzes word co-occurrence statistics across the entire corpus. So it counts how often word X appears in the vicinity of word Y throughout all the training text. GloVe essentially tries to combine the strength of those global frequency-based statistics, like TF-IDF, but more focused on co-occurrence, with the predictive power learned from local context windows that Word2vec used. It aims for the best of both worlds.
So we have these two giants emerging, Word2vec focusing hyperlocally and GloVe trying to blend local prediction with global statistics. But they both shared a massive fundamental weakness, didn't they? Something that really held back NLP for years. You hinted at it earlier, the problem of the fixed vector.
That's the absolute critical point. Both Word2vec and GloVe, despite their sophistication for the time, assign a single fixed vector to every single word in the vocabulary. Once the model is trained, the word run has one vector. The word bank has one vector, period, regardless of how it's used in a sentence.
And that works okay for words with just one primary meaning, I suppose.
Exactly. It's fine for aardvark. But what about polysemous words? Words that have multiple distinct meanings depending on context.
The classic example everyone uses is bank.
Precisely. The word bank. In the GloVe or Word2vec world, it has the same numeric address, the same vector, whether you're talking about a financial institution, I need to go to the bank to deposit money, involving concepts like finance, accounting, loans, or whether you're talking about the edge of a river. I'm sitting on the bank of the river, involving water, erosion, geography. The model couldn't distinguish. The vector was identical.
Which means basically every AI system relying on those fixed embeddings was inherently missing perhaps the most crucial part of human language, the nuance that comes from context.
Absolutely. It was a major limitation.
And that realization, that limitation, brings us to the biggest evolutionary leap in this field in the last, say, 5 or 6 years. The introduction of transformer models. So what is this new technology, these transformers, what does this all mean for how embeddings work now?
It completely revolutionizes the concept. We move from static embeddings to what are often called contextual-based embeddings. Instead of assigning one fixed address, one fixed vector to a word like bank for all time, the transformer model calculates the embedding dynamically for every single instance of the word as it appears in a sentence. It looks at the surrounding words.
Meaning the actual numeric representation, the vector for the word bank, physically changes depending on the sentence it's in.
Yes. Exactly that. In the sentence, I'm going to the bank to deposit money, the transformer generates a vector for bank that places it firmly in the financial neighborhood of the vector space, close to money deposit account. But in the sentence, I'm sitting on the bank of a river, the model generates a totally different vector for that same word bank, placing it much closer to river, water, erosion, geography. And this ability to capture nuanced, situation-specific meaning based on the immediate context. That's why transformer models like BERT, GPT, and others have caused such sweeping improvements across basically every NLP task. From generating much more coherent text to significantly improving machine translation accuracy, understanding sentiment better, it's the difference between having a static dictionary definition versus a dynamic conversational understanding.
It truly is an incredible journey when you lay it out like that. We went from, simple counting of word frequencies to
Mhm.
creating a single fixed coordinate for each word based on prediction, all the way now to a dynamic context-sensitive coordinate that literally shifts its location in that meaning space based on the sentence it finds itself in. Word embeddings in all their forms are really the proof that transforming our messy words into a powerful numerical format is the essential first step for machines to make sense of our incredibly complex linguistic world.
Absolutely. And I think that journey really shows that often the greatest advancements in AI don't necessarily come from just teaching the machine more facts, but from giving it a more accurate, more nuanced way to represent the knowledge it already has access to. Representation matters.
So as you go about your day today, maybe interacting with AI, whether it's just a quick search result or using predictive text or talking to a complex chatbot, try mulling over this idea for a moment. Consider how much of our own human understanding of a single word, like bank or run or set, is actually derived from the entire history of its use that we've encountered throughout our lives. We don't really understand words in a vacuum, do we?
No, not at all.
We understand them in the full, rich context of all our linguistic experiences, all the sentences we've ever heard or read. And it seems like that full context is just as critical for us humans as it is becoming for our most advanced AI models.
Well said.
Thanks for diving deep with us today.
My pleasure.
We'll catch you next time on